Alright, in this video we're going to look at example 3-5 out of the Shigley textbooks and copied into my notes. And basically it's how to handle, a quick review on how to handle composite moments of inertia. So we have a beam which is a T-section. The dimensions are given. It will undergo a bending moment of 1600 Newton meters and cause tension in the top surface. We want to locate the neutral axis and find the maximum tensile and compressive bending stresses. Bending stresses are no big deal. The big deal, of course, is finding the moment of inertia. And so, first thing we need to do is work out moment of inertia and work out the centroid. I've got sort of very small in my notes something that says the location of the centroid relative to a coordinate system where we're going to be measuring stuff is the area of region 1 times the location of the centroid of region 1 all by itself, plus the area of region 2 times the location of the centroid of region 2 all by itself, divided by the sum of those two areas. And of course, if we had more rectangular cross sections, we just keep going with the summations in the top: area 1, area 2, area 3, area 4, etc. And so we have two areas, one which is 12 by 75, and the centroid of this one would be halfway through the thickness of 12. Then we have another area of 12 by 100 minus 12, which is 88, so 12 by 88. And half of 88 would be 44, so the centroid would be located 44 from the bottom, or 54 from the top surface. So I'm going to use the top surface as my reference for measuring the y-bars. It'll also then be my reference for locating the centroid. And so to execute this sum, I'm just going to pop over to a little MathCAD sheet that I have hiding here that I did a moment ago. The first region's area is 12 by 75. The second region's area is 12 by 88. The location of the centroid of region 1 is measured 6 from the top. The location of the centroid of region 2 is measured 56 from the top. And if I go with A1 times y bar 1 plus A2 times y bar 2 divided by A1 plus A2, we get a 32.99 distance, which is the location of the overall centroid measured from the same place that I measured these two centroids, which would be from the top. So 32.99, and that is shown as the answer. Although this wasn't computed, it's shown as the answer. Now to get the moment of inertia of the structure, we will use the moment of inertia of this shape about its own centroid, and the moment of inertia of this shape about its own centroid, and then we'll use parallel axis theorem to move them to the centroid of the overall cross section. And so a BH cubed over 12 for region 1, where B would be 75 and H would be the 12. I didn't check the numbers, but I'm going to trust the 1080. And for region 2, BH cubed over 12, the H will be the tall number cubed, and the B will be narrow, so it's the 12 times the 88 cubed. And that looks like it comes out to be 6.8 times 10 to the 5th. These are the moments of inertia of each rectangle about their own local centroid. Parallel axis theorem says we can take the moment of inertia about its centroid and move it somewhere else by adding in the area multiplied by the distance that we're going to move it. And we're going to take this area, which was computed earlier, or this moment of inertia right here, plus this area which we computed earlier, and the distance we're going to move it would be the distance of the 32.99, which is basically 33, minus the 6, which is the location of this one. And so let's look at the formula that we have here. The 1080, the area 12 by 75, and 26.99 is the distance we're going to move the centroid from the middle of the rectangle to that centroid place. Okay, that is the moment of inertia contribution of the first region. Moment of inertia contribution of the second region is its moment of inertia about its own centroid plus its area 12 times 88, and this distance 54 minus the 33, basically. Let's see, sorry, 56 minus the 33 will be incredibly close to 23. That's the distance we square. adding all of this stuff up, we get a 1.9 times 10 to the 6 millimeters to the fourth. That would be the moment of inertia of this cross section about its own centroid, and that's what we need to do any stress computations. So we can do an MC over I. The moment was told to be 1600, and if we want to calculate the stress at the upper fiber, the C distance would be the 33, and so M times the 33C distance divided by the overall moment of inertia, 27.7 megapascals, and the distance from the centroid to the bottom fiber, which would be the other stress state, would be 100 minus the 33, and so that's going to be pretty close to a 67. And so M 1600, C 67 times 10 to the minus 3 meters, I 1.907 times 10 to the minus 6, or in this case a compressive loading of 56.22 megapascals. And the key thing, of course, is that we calculated the moment of inertia of a composite section. We calculated the centroid of a composite section using the centroid formula, and then we were able to use that to do stress analysis.